Hello everyone, welcome to a lecture on microprocessor systems and interfacing. My name is Dr. Vilayat Khan. I'm an assistant professor at Concepts University, Islamabad, Ba campus. These slides have been edited from these two sources given here. The topics of this lecture are instruction set of Intel family of microprocessor with the focus on instruction set of 8086 microprocessor, and some logical instructions are also part of discussion in this lecture. These logical instructions are test, shift, and rotate instructions. Microprocessors, and in particular 8086 microprocessor, supports 6 types of instructions. These types of instructions are data transfer instructions. These instructions are responsible to move or transfer data from or to memory, and from or to registers, and from or to input and output devices. And the second group of type of instructions is arithmetic instructions. These instructions are responsible to perform arithmetic operations, for example, addition, subtraction, and division. And the third group of instruction is logical instructions. These instructions perform logical operations, for example, logical AND, logical OR, exclusive OR. And the fourth group of instructions include string manipulation instructions. These instructions manipulate string data. For example, MOVS instruction that moves data between two memory locations, and the string data between two memory locations. And the fifth type of instructions is processor control instructions. These instructions control microprocessor. For example, setting the carry flag or clearing the carry flag. Similarly, setting the direction flag and setting the direction, clearing the direction flag. And there are many other processor control instructions. And finally, control transfer instructions. These instructions are responsible to transfer the flow of control from one place in the program to another place. For example, jump and call instructions are in this type of instructions. Among logical instructions, there are a number of instructions, for example, AND, OR, exclusive OR, test, shift, and rotate instructions. But the focus of this lecture are on test, shift, and rotate instructions. Test instruction is similar to AND instruction in operation, but the main difference of test and AND instruction is that AND instruction perform logical AND operation on two numbers or two sequences of bits, and the result is stored in a destination. But test does not store the result in the destination, or in other words, it doesn't change the destination. So it is similar in operation to AND, but the only difference is that test doesn't change the destination. The result is not stored anywhere. And test instruction only affects the bits, some bits in the flags register of the microprocessor, and then control transfer instructions are then used to transfer or to control the flow of the programs or flow of the microprocessor. Using jump instructions are then used to take decisions based on the new values or the updated values of the flags bit that have been changed with the test instruction. There are different forms of test instruction, just like AND or an exclusive OR instruction. For example, in the first form, the two operands can be register and the two operands can also be memory locations, but they cannot be memory locations at the same time, just like the AIM instruction. When in the first kind of instruction in this form is test register and registers are the two operands. So the two input values are the two sources of data are the two registers, and the values in these registers are ANDed, but the result is not stored, but only some flags are modified as a result of this AND operation. In the second form, the one of the operand is a memory location while the other is a register. And in this case also, data or value from this memory location is ANDed with data or value from this register, and the some flag bits are modified as a result of this AND operation. While in this third form, the first operand is a memory location while the second operand is a register. So the two values in this register and this memory location are ANDed, and this operation then modifies some flag bits. Test is also available with immediate data, where one of the operand is immediate value, while the other operand is a register or it is a memory location. If it is a register, then the immediate data is ANDed with the value in the register, and this operation then modifies some flags. While in the second case, the immediate value is ANDed with the value from the memory location provided here. So just like other instructions, whenever a memory location is used or memory is accessed, those memory addressing modes can be used. For example, here in this case, the offset address can be provided directly just by giving 16-bit offset address and enclosing it in brackets would make it a direct memory addressing mode. While if the same offset address is stored in a register and that register is enclosed in the brackets, then that would be a register indirect addressing mode, and similarly many other addressing modes can also be included. So whenever there is a memory in these instructions, a number of other memory addressing modes can be included. Test with immediate data specifically is also available with accumulator. In 8-bit version, the AL register is used with immediate data, and in 16-bit mode, the 16-bit part AX register is used for 16-bit data. And as these formats are specifically for 8086 microprocessor, but for other microprocessor accumulator, even 32-bit version or 32-bit registers of the accumulator, which is EAX, can also be used with immediate data. There are other examples of test instruction, and these examples are for latest microprocessors as well. So this instruction operates in 8-bit mode, where 8-bit DH register is ANDed with the 8-bit DL register, and the result affects the flags bit. And here test instruction is used in 16-bit mode, where the 16-bit two registers PX and CX are ANDed with each other, and some flags are affected. And here 32-bit mode is used, where 32-bit registers are ANDed. And remember that these registers are not available in 8086 microprocessor, so this instruction cannot be executed over 8086 microprocessor, but this instruction is compatible with 80286 microprocessor and later microprocessors. Similarly, test is available in the 64-bit mode as well, where a register 15 is ANDed with RDX, which is a 64-bit register, and it is also available with immediate data as well, where immediate value 4 is ANDed with the H register, which is also again an 8-bit register. So the two 8-bit values are ended and the result affects the flags bit. And here 256 is a decimal value, and this is ended as a 32-bit value with the 32-bit value in EX register, and the result modifies some flags. Here is a simple example with of assembly language program that is also using some jump instruction based on the result of the test instruction. So here test AL comma 1, this one is an immediate value, and this is provided in decimal. In the binary it would be 7 zeros and then 1. So as this is an AND operation, this will test the rightmost bit of the value in the AL register. And based on this AND operation, here we have a jump instruction. So right is a label somewhere in the program, and J and Z, which is jump if not 0. So if the result in this AND operation is not 0, then the program control will flow. The program flow will transfer to this right label and within the program. So jumps if the bit is set. If the bit is set, then the result will not be 0. And it happens like this. The 8-bit value, we are not sure about 8-bit value, so we just represent it with 8x's. And as I said earlier, the test instruction performs AND operation, but the result is not stored, but only affects flags bit. And 1 in the decimal is equal to 00001 in the binary. So this 8-bit value in the AL is ended with this immediate value given here. So the AND operation would give us this result, and the unknown bit here is not changed here. It is represented here, and we are not sure. If it is 1, then we get 1 here, and if it is 0, we get 0 here. And we are sure that as the rest of 7 bits in this mask are zeros, so in the result we will get all these 7 bits as 0. So we are sure that all these 7 bits are zeros, and only this bit is important. So if this bit is 1, then we get 1 here, and the result is not 0. So we can easily say that jumps if the bit is set. If this bit, rightmost bit, is set, that means if it is 1, then the result is not 0, and jump if not 0 would be true, so it would jump, and otherwise it would not jump. So this instruction tests the rightmost bit in the L register, and based on that we can jump or not jump. Similarly, the second instruction here, the test L comma 128, as L register is an 8-bit register, so 128 in the binary can be written as follows: 10000. So all are zeros. The right 7 bits are zeros, and the leftmost bit here in this number is 1. So it would it is sufficient to test the leftmost bit of the value in the L register. So we get 7 zeros here in the result, and an X at the leftmost position, and this X is the 8th bit, or the leftmost bit in the value in the L register. So if it is 0, we get 0 here. If it is 1, we get 1 here. So if it is 0, we get 0 here, and the result is 0. And if it is 1, then we get 1 here, and this will make all this value as non-zero. So jump if not 0, left, means it would test the leftmost bit, and if it is set, or if it is 1, then it would jump to a label in the program, and that label is left. So we can choose any bit in this AL register to be tested, and we just provide a value in the decimal or in the hexadecimal or in the binary here, and we can then test the corresponding bit, and then we can take a jump or to one place or to the other based on the result. Okay, so here we have some shift instruction. Shift. There are two kinds of shift instruction: shift right and shift left. But there are two forms of each of these shift instruction. One is shift, logical shift left, and the other is arithmetic shift left, represented as AL. So this is shift left, and this is logical shift, and this is shift left, but A stands for arithmetic. So this is arithmetic shift. And similarly for the shift right, we have shift right. This is logical shift right, and this is shift right, but it is arithmetic. A stands for arithmetic. Shift left and shift left logical and shift left arithmetic are the same, as these diagrams shows. But shift right and shift right arithmetic are slightly different from each other. So here the target is always a register or a memory, because the result is always stored. So shift left or shift right, shift left or shift right instructions, we have to provide a register or a memory location as a target. So that target is also the source of data as well, and that value in that register or the value in that memory location is left shifted or right shifted by a number of places. That is also provided as part of the instruction. We will see some example, but first we have to understand what is how these the positions of these bits are changed when shift right instruction is used and when shift left instruction is used. So with shift left, logical shift left, and arithmetic left, shift left instruction, each time the value in the register or memory is left shifted by one place. A 0 is inserted at the rightmost position of the value, and the leftmost bit is moved or copied to the carry bit in the flags register. So for example, if we have an 8-bit value here, and if we shift left that value by one place, then this bit is moved to the left and the final bit is moved to the carry flag, and a 0 is introduced at the rightmost position, and the same happens with this shift left arithmetic. In case of shift right, each bit is shifted right by one place. When we shift right by one place, the value or in the register or in the memory location, and rightmost bit in the shift right is moved or copied to the carry flag, while in the logical shift right, a 0 is introduced from left side to the most significant bit position here. A 0 is introduced, and if we again shift right, then the updated rightmost bit is then moved to the carry flag, and another 0 is introduced at the most significant bit position. While in case of shift right arithmetic, the rightmost bit with each shift, the rightmost bit is moved to the carry flag, and each time the value in the register or in the memory is right shifted, the same bit at the most significant bit is replicated. So this loop indicates that the same bit is kept in its own place, in its same place. As in the arithmetic right shift, this bit is the sign bit, so it is always kept in its own place, and it is replicated with each right shift. Just like test instruction, shift right instruction is also available with the register and with the memory location. And there is an immediate value or C register, count register, that provides the number of places to be shifted. So the value that is being shifted is provided in the register or in the memory location, and the number of places to shift the bits of that value in the register or in the memory is provided through an immediate value, or that count is provided through the count register here. The two operands are separated by comma. For example, let's suppose this is an 8-bit register, and the bits of these registers are represented with B0, B1, B2, B3, B4, B6, B7. So this B0 is the least significant digit of this 8-bit value, and this B7 is the most significant digit of this 8-bit value. So in case of shift right, the most significant digit of this value is replaced with 0, indicated here. So this most significant, with each shift, most significant digit is replaced with 0. So a 0 is inserted here from left to right, and each bit n is replaced with the left bit bn plus 1. So for example, B2, B0 is moved to carry flag, and this B0 is replaced with B1 as this B1 is right shifted by one place, and B2 is shifted to this bit, B3 is shifted to B2, B4 is shifted to B3, B5 is shifted to the place of B4, B6 is shifted to B5, and B7 is shifted to B6. And this B7, the most significant digit, is replaced with 0. And this least significant digit, which is here, is moved to carry flag. So this is how shift right works. In case of this is when the shift right instruction used with 8-bit register or 8-bit memory location, but in case of 16-bit, the same operation in the same style happens, but only the number of bits are larger. So the same least significant digit is moved to the carry flag, and the most significant digit is replaced with a 0, and every leftmost left bit is moved to the right side. With shift left, as with shift right instruction, the value to be shifted is provided through a register, or it is provided through a memory location. So this is shift left, logical shift, and this is shift left, arithmetic. So the two instructions are slightly different, and as with shift right instruction, the count or the number of places the value to be shifted is provided as an immediate value, for example 1, 2, or 3, and it is also provided through a register, count register. So with shift left, this least significant digit is always replaced with a 0, and the most significant digit is copied to the carry flag, and each bit is left shifted by one place when we left shift at the value in the register or the memory by one place. If it is to be left shifted by two places, then first it is shifted by one place, and then it is shifted by one place again. So that would mean shifting by two. And the forms are very simple to understand. The 8-bit value, in case of 8-bit shift mode, the value 8-bit value is provided through an 8-bit register, or it is provided through an 8-bit memory location. In case of 16-bit mode, 16-bit registers are used, and in case of memory, 16-bit memory, two memory locations are provided. So the same memory addressing modes can be used as we discussed with test instruction and also mm, with other instructions like AND and move instruction. Here are some examples. These examples are available for 8086 and above microprocessors, but not all of the instructions are available with 8086 microprocessor. For example, this is shift left, logical shift left AX1. So this instruction would move the 16-bit value in X register by one place. So each bit is shifted left by one place. And this is shift right, logical shift right, where the 16-bit value in the BX register is logically shifted right 12 places. So that means that the value in BX register is shifted one place, but this process is repeated 12 times. And similarly, logical shift right ECX10, this is a shift instruction in 32-bit mode. This instruction logically shift right the 32-bit value 10 times or 10 places. This is shift left RX50. So this instruction logically shift left the 64-bit value in RX by 50 places. So this is 64-bit mode, and this instruction is not available in 8086 microprocessor. Even this instruction is also not available in 8086 microprocessor. This instruction is available in 80286 and above. This instruction is available in 8086 and above. This instruction is available in Pentium and above microprocessors. This is using memory addressing mode, where shift left arithmetic. This instruction shifts the value, the content of the data memory location addressed by this data 1 offset address by the number of places given in the CL register. So this CL register is an 8-bit register. This CL register has a value, and that value is, for example, the value in this CL register is 15. Then the content of this memory location is left shifted by 15 places. So this CL provides the number of places to be shifted the value in this memory location. Similarly, this is shift right RX CL. So CL is a register that would provide the number of places specified. So the number of places to be shifted is specified by the CL register, and the value to be shifted is provided in this 16-bit register RAX, this 64-bit register. This is shift right arithmetic SI, that is 16-bit register, and this 2 is numerical value. So the value in SI is arithmetically shifted right 2 places. Similarly, this instruction would right arithmetically right shift the 32-bit value in EDX by 14 places. And finally, we have rotate instruction. So with this rotate instruction, mainly there are two types of rotate right and rotate left. But then for each rotate, there is a rotate left, and there is a rotate left through the carry. So this is rotate left through the carry, and this is rotate left. And similarly, this is rotate right through the carry, and this is rotate right. In case of rotate left through the carry, the value in this register in the memory location is rotated by one place, and this rotation is towards the left side, and the leftmost bit here with each rotate is moved to the carry. So that means rotate through the carry. So the leftmost bit is moved to the carry, and the carry is moved to the rightmost bit of the value. So this is rotate but through the carry. So the rotation passes through the carry. While in the rotate left case, the leftmost bit is moved to the carry, but this rightmost bit is updated from the leftmost bit at this value. Here, this rightmost bit is updated from the carry, but here it is updated from the leftmost bit. So this line passes through the carry here, but here it doesn't pass through the carry. So so this is the only difference between these two instructions. This is rotate left through the carry, and this is rotate left without passing through the carry. And similarly, with the rotate right, we have rotate right through the carry. So with each place rotation, the rightmost bit is moved to the carry, and the carry bit is copied to the leftmost bit or most significant bit of the value. So with each rotation, the carry is moved to the leftmost bit, and the rightmost bit of the value is moved to the carry. And in case of rotate right, the carry is bypassed, the carry flag is bypassed. With each rotation it is updated, but that value is not moved to the leftmost bit, just like with the rotate left without passing through the carry. With rotate right through the carry, the operand, the value to be rotated is provided through the register, or it is provided through the memory location. And the number of places of the rotation is provided through an immediate value, or it is provided through a register. For example, rotate right through the carry, and the value to be rotated is provided and specified in this register. Then comma, then the number of places to be rotated is provided as an immediate value, or it is provided through the count register, CL register. For example, here we have an 8-bit value stored in the 8-bit register or stored in 8-bit memory location. So in case of rotate right through the carry with each place of rotation, the carry flag is updated with the least significant digit. This least significant digit, B0, is copied to the carry flag. That is what we have identified here. And the carry flag is moved or copied to the most significant digit. So the carry flag is copied to the most significant digit. And each left bit is copied to the right position. So B up n plus 1 is copied to B up n. For example, B1 is copied to B0, B2 is copied to B1, B3 is copied to B2, B4 is copied to B3, B5 is copied to B4, and B6 is copied to B5, B7 is copied to B6, and this B7 is updated from carry flag, which is represented with this arrow. And the same procedure happens with 16-bit value, just the number of bits are more. And rotate right through the carry is also operating over the memory location, and this memory location can then be used with a number of other memory addressing modes. And this is rotate left, where the value to be rotated is provided through a register, or it is provided through a memory location. With rotate left instruction, each bit is left shifted by 1, and then the most significant bit, which is an B7, is copied to the carry flag. Most significant digit is copied to the carry flag. The carry flag is copied, the most significant digit is also copied to the least significant digit. So the most significant digit is copied or moved to the least significant digit, and Bn is copied to Bn plus 1. So each bit is copied to the next higher bit or left bit of each bit. So B0 is copied or moved to B1, B1 is copied to B2, B2 is copied to B3, and so on and so forth. And the same procedure happens for 16-bit rotate instruction as well. And remember that These 8-bit mode and 16-bit mode are available with 8086 microprocessor, but with later microprocessor, even the 32-bit and 64-bit modes are also available. Here are some examples for 8086 and above microprocessors. Rotate left SI14, so this instruction would rotate left the 16-bit value in SI by 14 places. So it is actually rotating SI by one place, but this process is repeated 14 times, so we can interpret this instruction that way. Rotate left through the carry BLCX, so this instruction would rotate left through the carry the value in BL register by 6 places. And this is a 32-bit mode instruction, so rotate left E6 18, so the 32-bit value in E6 is left rotated by 18 places. And this instruction would rotate left the 64-bit value and the rotation would be 40 places. So the rotation shown earlier are representing the rotation by one place, and the value here are larger, so that rotation is repeated 40 places in this case, and in this case that rotation is repeated 18 places or 18 times. Here rotate right through the carry, so the value in this H register is rotated right through the carry by a number of places specified by the value in the CL register. And this rotate right would rotate right the value or the word content or 16-bit value in the data stack segment memory location addressed by this offset address stored in the base pointer, and that value 16-bit value is rotated right by 2 places. And this word Ptr Directive is used to tell the microprocessor that the value to be rotated in the memory is a 16-bit value, and if it would be a single byte value, then byte Ptr is used, and there are other directives for if the value is larger than